So in this video, I'm going to go through the equations required for the force vibration topic, specifically how to get x as a function of time for the force vibration. So just to remind ourselves of the difference. So free vibration occurs when you have no external forces applied to your system. The only reason that you get vibration in these cases is you have a displacement, an initial displacement I should say, away from the equilibrium position, or an initial velocity or an initial acceleration. For force vibration, the difference is that you actually have external forces applied to your system, and these are going to force, as the name suggests, your system to vibrate. So if we just think about the equation that we get out when we sum our forces to be the mass times acceleration in either cases. So for the free vibration, we get something that looks like this. And the key thing to note here is we get a 0 on one side of the equation. And for force vibration, we end up with an F instead. That F, it represents the applied force itself. So in this unit, we're only going to be looking at one specific type of forcing function, and that is when our force is equal to Fo sine omega t. So Fo is the magnitude of that function in newtons, and omega is its frequency in radians per second. So yeah, again, we're only looking at this one type of forcing function. So for these force vibration questions, you want to try and solve typically for x as a function of time, and that's how your mass vibrates over time. And when you have force vibration, you need to find two components. Okay, so this first one here is the xh, or homogeneous component, and this one here is the particular component. So this homogeneous part comes about due to the free vibration, so I'll put in brackets here free component, and the particular part is attributed to the forced component. So when you solve the free vibration questions, really all you're doing is solving for this homogeneous part, the free component. Your particular solution ends up being 0 because you have no force component. So when we introduce that force component, obviously then we need to actually solve for this specifically. So I'll just quickly run through the steps required to solve for x as a function of time. And it's very similar to what we had for the free vibration, except we've got kind of that one extra step with the xp component. So we said that the first thing you want to do is draw a free body diagram. And from that free body diagram, you want to sum your forces to be equal to the mass times the acceleration. Then you want to use your general form of your equation to find your damping ratio and natural frequency, remembering that general form is, should be 2 omega n theta. So that's what the general form looks like. And you can equate it to what you get out of step 2. Alright, so this is where it changes a little bit. You want to find the xp, or the particular part of your solution. And the trick here is, if we know that we've got a sine input function, we can simplify down the particular components to something that's actually quite easy looking. We're not going to be expecting you to solve these from scratch, these differential equations. So for xp, if we have f equals Fo sine omega t, we know that the form of xp is going to look like this. Okay, again, only applies this type of form for ones that look similar to this. Alright, so we have two constants in this equation that you're probably going to need to find. So one of them is this big X, and the other one is phi here. And again, if you want, you can derive out the expressions that I'm about to give you, but yeah, again, we're not expecting you to do it from scratch. So if you want to just cut the derivation step and sub in, that's perfectly fine. So if you go ahead and solve for the constants, it simplifies down to something like this. Oops, let's give it a nice bracket. Okay, so we end up with FO, that's the magnitude of your forcing function. This here is K total, so the total stiffness in your system. We end up with the frequency of your forcing function, the natural frequency of your system, and your damping ratio in here as well. So phi, again, we have an equation we can use. Okay, again, these are all made up of constants that you should have solved for before. So once you solve for these numbers, you can put them back into your XP equation, and the question returns to basically the normal procedure that we use for free vibration. So the next thing that you need to do is choose the form of XH. So remember, this is your free vibration part, based on your damping ratio. And if you're unsure of what that needs to look like, go back and see the video for equations in free vibration. There's 4 different options for what X of H looks like, depending on what you find for your damping ratio, and whether you have undamped, underdamped, critically damped, or overdamped motion. And the last thing is to solve for the constants. From the initial conditions that you're given. Okay, and that should give you your equation for X as a function of time. So the only other thing I wanted to mention was what happens at steady state for your system. So at steady state, free vibration is damped out, so only forced vibration remains. Okay, and just a reminder, this is only going to apply when your damping ratio is greater than 0. So you've got some form of damping on your system. Otherwise, you're just going to have the system vibrating forever and ever, and that will be its steady state. So provided that we have damping in our system, steady state is going to occur as time goes to infinity, and we know that that means that XH is going to go to 0, and that's our free vibration component. So if we know that X is equal to XH plus XP, and this is going to 0, at steady state we can just directly equate these. So our overall displacement is just going to equal the particular component. And just to give you a little demo of that, what it looks like on a graph, if we plot X versus time, let's say that we have an underdamped system, so we would expect our motion to look something like this. Vibrates above and below the axis until it is basically 0. So that's going to be our XH part. And let's say we have a sine input function. We would expect this to vibrate back and forth forever and ever and ever and ever and ever. Okay, so that's XP. So you can see that as time goes to infinity, XH basically becomes 0. That's what it's supposed to be, because it's been damped out, and all that remains is XP. So basically we have steady state here, and you can see that the only part, or the dominant part here, is XP. So that's why we can say that. So that's all I've got. See you next video.